Hello everyone, I wanted to show you a model of food production. So we're here in the Lecture 11 folder, and I'm going to open up the Vensim model for this food production system. And you can see the model is pretty involved. I left some space here to plot some graphics as we run the model. But I wanted to show you a little bit of what the model is about. This is an interesting food production model because it basically looks at the competition between vegetable oriented food supply versus livestock oriented food supply, how those two compete to sustain a population, and the trade-offs that may be involved. This model was actually based on some real data from Germany, and in this case, some policymakers in Germany about a decade ago were looking at ways to move the population from a more livestock-oriented diet to a more vegetable-oriented diet over a period of 10 years, I believe. We'll actually see the model, and doing a shift, and then see what will be the impacts of that. So this is a simplified version of that model that I took the original simulation model and simplified it a little bit for the class, but I'll tell you later when we look at the structure of this model, what else could we do, because I think it's a very interesting model. I think the other piece of why I liked it so much to show in this class is because it actually, this model, as complex as it seems, as we'll walk through in a second, it actually doesn't employ any complex mathematics. I mean, all the relationships in every single one of these equations is fairly straightforward. It's algebraic, so no exponentials, no logarithms, no complex math. It's very common sense oriented. So I like that for that reason. But let me tell you a little bit about it. The model has 4 stocks. The first stock is population. Okay. And of course, population, as we've seen before, there's births and there's deaths associated with them, and we'll talk a little bit about that. Now, population is fed by a combination of a vegetable-based diet, exemplified here by the grain supply, and livestock. So, meat, milk, eggs, everything that's animal originated, it's on the livestock. Everything that's vegetable originated, it's in the grain supply. Now, of course, in order to grow livestock for human consumption, grain vegetables must be used. So there is an interesting trade-off, because the vegetable part of the diet is actually used both to supply the population directly and also to feed the livestock that will then supply the population. So as we move towards a less livestock-intensive diet, that will allow us to consume more grains, but the trade-off doesn't stop there, because of course growing livestock doesn't just involve grains. It also involves another source, which is land, okay, and grass that grows on land. So as you move from more towards more vegetable-based diet, less livestock-based diet, there'll be a trade-off on the amount of land that's needed to grow the grains versus the amount of grass, that is needed to grow the livestock. So that's a little bit of that dynamic, and that's the 4th stock, the arable land. So again, 4 stocks: population, grain supply, livestock, and the arable land. Okay, so let's walk a little bit through the dynamics and see how the model is structured. You'll see that like these complex models that we've been looking at in the class, I mean, they're fairly involved. But actually, once you understand the logic, the interesting thing for you in the learning process is that you're able to pick up some tips and tricks and how things are done. Okay, and hopefully this will help you in your term project. And I think I've mentioned this, and I'll say it in my commentary. you know, the scope of your term project is not something like, you know, like this. This is a fairly, even though it's a simple model, it's a fairly complex interaction, and it's, I can tell you, this was not developed by a single individual. This was, you know, groups of people or groups of specialists in each area working together, and that's the common approach in system dynamics, and it's also the power of system dynamics as an integrator of disciplines. So that's why, you know, I think this learning it's actually useful for you. So let's walk through the model. So start with the easy one, population. So population, in this case, population is very, very straightforward. There are births and deaths, and the births are driven by a birth rate, and the deaths are driven by a death rate, and there's really no relationship between the births and the deaths and the diet, okay, which is probably questionable, and you can start already thinking about the ways you could actually change that. But so right now, population is pretty much sort of running as a driver of the dynamics between the two main food supplies. So now, what population does do, though, is that population generates food demand. So population, you know, whatever value it has, it generates a demand for food. Okay, so that's where the population enters into the dynamic. Okay, if you look quickly at the equations for population, I'm going to show you just a stock. It's straightforward. It's you know, births minus deaths. You know, very easy. It's initialized by an initial population, and I believe the initial population is something like 80 million, which is you know, a characteristic of Germany in the you know, at the start of this simulation. Now, before I go into the dynamic, let me look at the targets for the goals in the vegetable fraction and diet. And the idea, and there's a couple of variables here. There's a begin diet conversion. So this is the year at which the diet conversion is supposed to begin. So this is going to be done over a period of time. And if you look at that equation, this is 2005. So in 2005, you start with and then I'm sorry, before we go into that, in 2015 you end the conversion. So it's a process that takes 10 years to convert, and you go essentially from and this is the equation for the conversion, and this is the equation of a straight line. And the idea here is that between 2005 and 2015 you convert the diet from 60% based on vegetable originated foods, which means 40% livestock. So raise that to 90% vegetable originated foods, and then 10% livestock over a period of 10 years. So that's the target. Okay. So that's basically this statement here. This is essentially it's a linear relationship. So at 2005. You're supposed to be at 60% vegetable. In 2015, you're supposed to be 90% vegetable. And during the interim, it's a straight line or a straight trend. So the idea is to convert this population with given birth and death rates over 10 years from 60 to 90 in terms of the supply of food from vegetable origin. Okay, so that's the setup of the problem. So so population generates a food demand, and then, you know, the shifting of that food demand is what's going to bring about the dynamics between, you know, livestock and grain supply as sources of food. Okay, so let's take a look at how the logic goes. So population generates food demand. Okay, and the food demand basically triggers a couple of variables. It first triggers the fraction of vegetation in food. So if we look at that equation there, it's the fraction of vegetation. It's referred to here as a ratio between the residual demand for vegetable food divided by the food demand. This residual demand for vegetable food is essentially the amount of food that's demanded by humans. It's called residual because it takes out, or it subtracts, the demand for food by livestock. Okay, so this is the so if you take this ratio, this basically tells you that this is the amount, this is the fraction of food that's originated from vegetables. So this is the fraction that you want to bring up. Okay. Now the food demand. So this is where the residual is. So let's take a look at how this residual demand is computed, because that takes us to the livestock. The livestock stock. No pun intended. Livestock, like any population, has a growth rate and a in this case it's not a death rate, but it's actually an output rate of livestock, which is essentially the output of livestock becomes food. Okay. Of course, that food, once you know how much food is produced to be consumed by humans, then you can compute this residual for vegetable food. Okay. And here there's a couple of coefficients here that are used to essentially convert the amount of livestock, and the units of livestock are here are cattle units. So I'll actually look at that equation here. See, the units are MCUs, which are probably millions of cattle units. So these cattle units then are converted to essentially food to humans, and food to humans is actually, in this model, is converted to calories, or to kilocalories, which is what is used to compute, human feeding and human growth, like we've done before with our very old, at the beginning of the class, human body model. All right, so let's go back to the livestock. So livestock growths and gets produced for sale, essentially, as food, and that in growing this livestock, you will see that there's a demand for. This creates a residual demand for vegetable food, because and we'll go to the grain supply in a second, but essentially cattle are fed by a combination of grains and grass. Okay, so once that demand is known, then this residual demand for vegetable food drives the production of grains for human consumption. So we're going to get to that in a second, but let me wrap up the livestock dynamics here. The livestock are, if you look at the growth part of livestock, the growth of livestock is originated by a couple of sources. One comes from the grains, and we'll see that in a second. The other comes from the grass. Okay, so there's a production of grass in the land, and we'll go to that also when we talk about the arable land. But there's a production of grass which produces essentially this fodder, and fodder is this it's the basic feed that is grass originated for livestock. Okay, for cattle primarily, so that fodder essentially produces generates livestock growth through a set of dynamics that are here. The fodder production it's generates available grass. Okay, now the available grass is the grass is available to grow cattle, and that is basically the whole grass production minus what's used to grow the grains. Okay, so once that available grass is known, and then here you have essentially what's called a desired change of livestock. So this is the amount of livestock from the current conditions, the conditions in 2005, that you want to change. Okay, so like we said before, the idea of this model is to explore a lesser consumption of livestock. Okay, so this desired change of livestock, it's what produces is that change, as we'll see in a second, this change is going to be negative, because the diet is being driven for less consumption of livestock. Okay, so that basically takes care of the of the livestock growth, and then let's look at the livestock sales. Then those drive food for livestock production, which generates this residual demand for vegetable food, which then of course drives the consumption of grains for food. So let me move on to the third stock, which is grain supply. Okay, now grain supply, if you look at the ins and outs, there's a harvesting of grains for growing. Okay, and there are imports. There's the capacity to imports, or actually exports here. So this economy, or this production system, has the ability either to import or to export grains. Okay, so positive imports are grains coming into the system, and negative imports are actually exports outside of the system. So harvests and imports are ins, and then there's two outs. There's grain consumption for food. Okay, so this is basically the idea of these grains is that these will feed humans. Okay, and then there is the grain production to feed livestock. Okay, so let me take a look at this piece first, because actually the grain consumption for food is sort of the target. So we can take a look at that towards the end, and we can actually graph this. But let's take a look at how the grain supply produces feed consumption for livestock. Okay, so this essentially gets translated into to a feed volume. Feed volume is essentially a requirement to grow livestock, and that goes, see, the feed volume goes straight to the livestock growth in addition to the grass. So here you see the two sources causing livestock growth. One is the grains through this feed volume, and the other is the production of grass. Okay, and that's how that dynamic is closed. Then we can take a look at the the production of grain, the harvest, gets essentially fed or produced by plants, by plant growth. Okay, plant growth requires land. Okay, and essentially the idea is that the more or less grains are produced, the more or less arable land you will need. Okay, if you look at the change in arable land, there's a couple of variables that appear here. And you have an upper limit and a lower limit. So this here, it's meant, the upper limit and lower limit are tricks that you've seen in other models before. These are used to establish boundaries on the low end and the high end of how much land can be produced. And you do this essentially if for no other reason, it's just to make sure that your responses or your model simulations don't go out of bounds. Okay, so that you're not overshooting the use of land or undershooting the use of land, or going to values of land that are not realistic. Okay. Now there's an interesting dynamic here that I haven't mentioned in the arable land, is that if you look at how what's coming into the grain supply, these imports, depending on how much these imports are, or these imports are needed, then you have also another sort of a secondary trade-off between importing grains. So if you need more grains for supply, either for humans or for cattle, you can do two things. You can import more grains, or you can actually convert arable land to grow more grains. Okay, so that's another trade-off right there. The trade-off between importing and converting land for production. Okay, and then here you have the arable land stock. Couple of things. On the model itself, if you look at the settings of the model, you're going to see that the model is run from 2000 to 2025, so to cover the pre and post period of the diet conversion period, which is 2005 to 2015, and they use in this case time step is in years, so an eighth of a year, so it's basically like a month and a half of time step. Okay, you can play around with that if you want, just to see the results. I guess my sketch disappeared. There it is again. Let's see. So we can actually take this model and run it and look at some of the results and see you know, some of the interesting things that happen. So I'm going to run it as is, and then we'll go back. We'll come to, you know, to some of the questions that appear. So I'm going to simulate that, and so it went through the simulation very quickly. And I'm going to turn over to the graphs, and let's take a look at the first graph that appears here is the livestock. And I'm gonna look at a bunch of these, so just to give you an idea of what's happening. Let me look at population first, so we can look at them in order. So I'm going to graph population, and I'm actually going to move this livestock down. And so look at population right there. Here we go. So first of all, Germans, as well-known fact, have been, you know, the population is shrinking. So it's a different situation. Imagine, you know, now if you do this in a country where the population is growing. So the results are going to be interesting to see, and I'm going to ask you to do that. But the population in Germany, it's you know, it's growing, and the demographic rates are built into this birth and death rate. So that's this straight line is essentially a product of a imbalance between the birth and the death rates, where essentially the birth rates are much smaller than the deaths, so the population is going down. So no secrets there, fairly straightforward. Let's take a look at the livestock you know, and as a result of this, you know, you can see the sort of the you know, the two limits. So these are in, you know, million cattle units for any given year. And then what you have here is that you go, and remember the conversion takes place between 2005 and 2015. So you can actually see, you know, that the system actually just you're up here in the beginning, and then you're down here after the conversion. You're down to maybe 6 million cattle units as opposed to 18. So you're sort of cutting your livestock by you know, a factor of 3. So that's pretty significant. And then you can see that pretty much it's not completely a straight line, but pretty much the dynamics are straightforward down. Let's look at the other source, which is the grain supply. Okay, so I'm gonna, just so I can, I'm gonna move this up. Let me look at grain supply and graph it. There we go. The grain supply, of course, does the opposite. So the grain supply goes from negative, and in this model, the initial conditions of grain is that you're running at a grain deficit. That means that you don't have, interestingly enough, these guys were trying to switch to a vegetable-originated diet while having a deficit in their stock of vegetables. So so that's you know, that's a kind of an interesting thing to mention. And so the production of grains, essentially, or the stock, I shouldn't say the production, the stock of grains, because there's imports and all these other factors come in, it's bound to go up. It actually started going up you know, before 2005. The reason for this, you know, maybe had to do with the fact that, you know, population was decreasing. So there was something there happening before, but certainly, you know, as you move away, you know, you sort of go from a smaller slope to a pretty steeper slope here in the stock of grains. Okay, because the policies are being implemented there to produce this exact effect. Okay, so let me take a look at the last stock before we look at other variables, which is the arable land. And if you look at the arable land, interesting. So this is actually something that might not be expected, is that you actually were using much more land before the conversion, because it is more intensive to use the land to produce grass for the livestock, okay, which is up here. And these are millions of hectares of arable land. to using this, using land to grow grains, okay, to grow vegetables. Now, again, I'm going to couch that because this, and I want to look at the imports, because this might not be entirely a result of just switching land from livestock to grains, but actually may have there might be an issue there with the imports. Okay, if you increase imports, of course you're going to use less land. So we're going to look at the imports. But it was interesting to see, so hold that thought for a second. I'm going to keep these two graphs up, and I want to let's try to take a look at the imports. So I'm going to switch over to the imports and graph it. And interesting, see, the imports actually go down significantly. So before, and this is where the policy makes sense, you were importing a lot of grains to have a grain supply, so you can actually grow livestock, so you can feed population, instead of actually, and if you compare, I'm going to put this down here. If you look at the grain supply went up, and it went up so much that you're actually now doing negative. So after 2015, or actually pretty much when like right after the diet conversion started, you can see that the imports go negative, which means that Germany started to export grains, become an a grain exporter, just because of making this change, which illustrates the importance of switching to a vegetable, diet. Okay, so for you vegetarians out there, I'm pretty sure you're rejoicing in this interesting finding. Okay, again, let me recouch these arguments, these notions, on the fact that the population in Germany is decreasing at the same time this is happening. So there's less internal demand for food, and it won't compensate for the whole thing, but it should be mentioned as well. Okay, so grain imports are going down. Let's take a look at other. I'm going to get out of these graphs so I can generate some new ones. Let me look at the diet conversion itself, just so you see what it looks like. And it's essentially, so this is the vegetable fraction in the diet, going from 60% to 90%. So that's essentially the straight line that I was referring to earlier. Okay, over a period of 10 years. Okay. What else can we look at? Let's see. We can look at let's take a look at the arable land. I don't think we've done that yet. Well, actually, we did do that, but let's look at the production of a couple of things I want to look at. I think this was one, and of course I invite you to take a look at this. Well, this is a constant, so it's really not very interesting. Let me bow out of that. Let's take a look at the available grass when you do the conversion. So this is the extra amount of grass available when you switch over. So in this case, you're running a deficit of grass at the beginning, okay, and then towards the end, you essentially reach a situation in which you, because remember you're decreasing the livestock that's producing grass, you essentially get to a point where you reach equilibrium. So you really don't need any more grass, because you've actually reached a sustainable situation. See, you were running before an unsustainable situation, which you were converting a lot of land to produce the grains, to feed the cattle, to feed the livestock, to feed the population. So you're not doing that anymore. Okay. Let's get out of these. What else can we look at? Let's see. For the most part, a lot of the parameters are pretty constant. There is, let's see. So we've seen the livestock. I think that's pretty much it. I I want to ask you to look at a couple of questions that are posted in the model description that's posted in the lecture notes. So I'm going to switch over to that, so let me just here. I think the last page in the model description that we posted had a couple of questions, and I want to focus on the first one. I'm going to ask you to do a couple of more, but so this basically is this model allows you to investigate the consequences of transitioning to a more or less based meat-based food diet for different assumptions. So take a look, play around with the model. For example, you could change the initial and end dates of the conversion. You can modify the targets. Not necessarily 60 to 90, but you can do more. I think the second and third questions are a little bit. I mean, they're not that relevant, but it's okay. I think the fourth one is very relevant. So, what happens if you try to apply this model to a developing country? Okay, in a developing country where population is growing, for example, or try to apply it to a world as a whole. Okay, and the world as a whole is growing as well, and try to look at strategies for fighting hunger by changing the composition of the diet. Okay, and look at also the limited arable land limits, and try to see where that leads you. I also want to ask you to think about a couple of things regarding this model, and I think for example, there's no economics here. Okay, so even though we're looking at variables here, there's no. I think the economics of livestock versus grains may cause some of these dynamics to shift, and that's not in this model. So think about how would you add economics to this, and I'd like you to think about these things and post some discussions on our page. Even if you actually want to introduce some present value, future value, if you want to throw in some figures, try to see how these results could be impacted by economic driven policies, which are not here. So that's one aspect. I think the second aspect is not included here that would be interesting to look at is health effects. How does a combination of grains in livestock, how does that impact the births and the deaths of people? Okay, in terms of health variables, that's not here either, and it might again, it might not be relevant, but it'd be very cool to see if there's there's an effect. Okay, so those are a few closing thoughts. I think again, I want you to look at this model in detail. If there are any questions about how any part of the model is working on the equation, so I want you to go to this f of x box and start clicking around and try to understand all these different numbers. Read the model description that it's in the folder, so you can get a little bit of a perspective of how this was done, and ask any questions as well. So I want to see questions, I want to see clarifications, I want to see you guys experimenting with this and learning in the process. Okay, so I'll leave it at that. Enjoy the model, and I also will accompany this video with a little commentary on the lecture itself. Okay, thank you very much.